All right, hey guys, we're going to be looking at acids and bases, and this PowerPoint is designed to give you guys an overview as far as the basic parts of acids and bases, their basic properties, and how we measure them or how we kind of look at them. And then we have other PowerPoints and other videos that you guys can look at that will go beyond that. So, but if you look at this basic graphic, this kind of tells you a little bit about what you need to know about acids and bases in general, and that I tend to think of them as opposites of one another. Nature likes to be neutral. And so we look for a balancing act essentially between acids and bases, where one can neutralize the other. They tend to be opposite in that regard. So acids and bases only form when dissolved into water to form a solution. For example, if you have HCl, hydrogen's a gas, chlorine is a gas. The AQ that we have talked about before is what means aqueous solution. And in this case, hydrogen chloride gas dissolved in water, the new name is hydrochloric acid. So there's basically three ways that we look at in order to define what an acid or a base is. And there are a few different people that are involved in this. The first one we're going to really look at today is Arrhenius. And according to Arrhenius, the way that he defines it is an acid under the rules by Arrhenius, it's a person. The acids are defined as having hydrogen or hydronium ions in their solution. So you're going to look for things that are in the solution, compounds in the solution that have a hydrogen ion or hydronium ion in a solution. Bases, according to the same guy, Arrhenius, according to his rules, bases have a hydroxide mixed into the solution or metallic ions in the solution, and it has to be the OH together, okay? They have to be together. If you can't remember what hydroxide is, you can go back and look at that again. You'll also find it on the back of your periodic table. Alkaline is something you guys probably hear all the time. I'm sure you guys have heard of alkaline batteries and things like that. Alkaline just means base. So anytime you hear the word that says something is an alkaline, it means that it's a base. So what you're going to do is you're going to practice, and this is how it'll be on your test. You're going to practice whether each one of these is going to be an acid or it's going to be a base. So for the first one, which is the example that we just gave you, this is HCl. It's hydrogen and chlorine, which would be hydrogen and chloride if you combine them together under the normal terms, but now it's going to be an acid. So we know that it's going to be an acid according to Arrhenius's rules because it has an H. There's no OH, there's just the H. So it means that it's an acid. So you'll notice that that hydrogen ion is present. The second one is H3PO4. And this one is going to be an acid as well. Some of you guys might have guessed that it would not be, but it is. A lot of people want to say it's not because it's got the H and the O. But remember what we said? They have to be together. So the H and the O has to be OH together. In this case, you have hydrogen and you have oxygen. They are not together. So this makes it an acid. NaOH, sodium hydroxide, is a base. And you know it's going to be a base according to the rules of Arrhenius because the OH is together. And the fourth one is calcium hydroxide, also going to be a base because the OH is together. And then NH3 is neither, which is kind of a weird one. Why is that? That's a good question. We'll look at that in a second. Sometimes it's going to act as a base. Sometimes it might act as an acid. In this case, we would consider it to be neutral. So here's another person and another way that we look at acids and bases. So the first one was Arrhenius. This is Bronsted-Lowry. So these are two separate people, two separate definitions. And you would need to know, for the purposes of testing going forward, you guys are going to need to know, is something an acid or a base based on Arrhenius? And then you might have another question that says, is something an acid or a base based on Bronsted-Lowry? So according to Bronsted-Lowry, and these are color-coded for you guys, acids are hydrogen donors. And when you donate something, you guys love to talk about being an organ donor, I guess because you're getting your licenses lately. And a person as a donor gives something away. So acids, in this case, are hydrogen donors. That means they have a hydrogen, and they're going to give it away during a reaction. So they're going to form a conjugate base, okay? And this is all based on the idea that we have a reaction. Remember, you have the arrow to show that you're having a reaction, okay? So if you guys look at the animation here, you've got chlorine on your left-hand side. You see how it's the little green chlorine? Notice after the reaction, what has it done? At first, it has a chlorine and a hydrogen. It's HCl, okay? It's an acid, HCl, remember from the first example. Afterward, on the other side, you have 3 H's and you have an O. So that's H3O, not H2O, but H3O. And the chlorine has a -1 charge because it gave away its hydrogen. Okay, so it donated a hydrogen. Bases are hydrogen acceptors. Bases are hydrogen acceptors. That means they're like, hey, give me a hydrogen. I'll accept that from you. And they form a conjugate acid. Okay, so every time that you guys do these reactions, or every time that you guys are looking at neutralization reactions, or you're looking at the Bronsted-Lowry rule, you're always going to have an acid and a base on the left-hand side of your arrow, and you're going to have a conjugate acid and a conjugate base with all the big words on the right-hand side after your reaction. So here's how we're going to identify these as a base, an acid, a base, a conjugate acid, or a conjugate base. And remember what I said, you're always going to have the acid and base first and the conjugate acid and conjugate base after. You're going to add the word after the reaction. Okay, so here's your reaction. And in your reaction over here, you've got the HF. Okay, so you've got this element here plus water here. Here's your reaction, okay? And then here's what it forms after the reaction, okay? So in this case, let me go forward there. You're always going to look to see how the reactants change. Remember, the reactants are first, so look to see how your reactants have changed. So I've drawn an arrow here to show that you're going to go from this right here, hydrogen fluoride, and then afterward, you still have the F over here. This was your reactant, and how did it change? What's it missing in this case? It had hydrogen fluoride over here. It had hydrogen and fluorine. And afterward, what is it missing over here? Okay, so we know because it started out with HF and it ended up with an F. It started out as an acid because remember, according to Bronsted-Lowry, this guy donated his hydrogen. Afterward, you can't be an acid on both sides. If you start as an acid, you're going to end up as a base, but you end up as a conjugate base. So that means if that's the case and you end up as a conjugate base, what are you going to end up as here? So if you start out as H2O, that means that your water, H2O, is going to be acting like a base. After the reaction, you can't be a base anymore. You have to be a acid. And what kind of an acid are you going to be? A conjugate acid. Okay, so acid and base just by themselves on the left-hand side. Afterward, they become the opposite, and you add the word conjugate. So conjugates are always on the problem. So here you should pause this for a second and see if you can work through this on your own. So you've got H2SO3 plus H2O produces HSO3 and H3O. Okay, so you're going to have to figure out, starting right here with this guy on this side, over here, find the one on the product side that looks the most similar. So this has sulfur in it. So I would say that the one that has sulfur is this. So over here, he has 2 hydrogens. After the reaction, how many hydrogens does he have? He has 1. So did he pick up a hydrogen or did he donate a hydrogen? I would say he donated one, or he gave one away, right? And so if you donate a hydrogen, what does that mean you are? You're an acid. You donated a hydrogen. Afterward, you become a base, and a special kind of base called a conjugate base. Okay, and then that means that once you've figured out the first part, now you should be able to figure out this, because if the first part over here is an acid, what's the second part got to be? The second reactant has to be your base, because he's accepting a hydrogen. So now I can double check myself and go, okay, well, he has H2, and then after the reaction, what does he have? He has H3. So he must have picked up a hydrogen somewhere. So he must be a base. He's accepting the hydrogen, and then afterward, it's your conjugate acid. Okay, you don't have to figure out conjugate base and conjugate acid on your own. You have to look at it and figure out where did you start and what did you end up with. Okay, this is your second example. So pause for a second and figure this out. So same thing here, you start with H2PO4. So find the one after the reaction that has the most similar things in it, and that's going to be this guy over here. He's got phosphorus in it. So over here on this side, you have, over here on this side, you've got H2PO4, and then afterward you have H3PO4. So if you start with 2 hydrogens and you end up with 3 hydrogens, did you pick up one or did you donate one? So that means that you are accepting a hydrogen. So right here, he only has 2, and somehow after this reaction happens, he now has 3. So that means that he accepted, gratefully, a hydrogen. So that makes the other guy a conjugate acid. So then you have to look at your second reactant, which is water, H2O. And if the first part over here, H2PO4, acted as a base, then what does that mean the water is in this particular case? It's going to obviously have to be an acid. And an acid is going to donate a hydrogen. He starts out with H2O, and he's going to end up afterward with OH minus. So he is a conjugate. The next part of this is what we call buffer systems. And a pH is the scale that we use. I talk about pH in a separate lesson, but pH is the scale that we use to describe and measure whether a solution is acidic or basic. Okay, and if you guys remember from your properties of acids, there's a lot of different properties that they have. The way that we describe them, how strong they are or how weak they are, not just chemists, but you know, people who make soaps and when we test our water all the time, or when you guys are looking at the aquarium in the classroom, it always has to be a certain pH. And so this is how we measure that. The pH, anything that has a pH that is less than 7 is going to be an acid. 7 is kind of your magic number. It's your neutral pH. Bases are going to be greater than 7. Acids are always at the bottom of the scale. They're the lower thing. So the lower that you go, the higher your concentration of hydrogen ions, so the stronger of an acid you are. Okay, a buffer is a solution that really resists a significant change in pH. In other words, you can do what you want to me, but I'm a buffer and I don't want to change, so I'm going to make it really hard for you to switch my pH around. And buffer systems contain both an acid and a base. And they release, like for example, the human body will release an acid or release a base based on whatever is going on in our bodies at the time. And your body's kind of miraculous. It does this all the time, every day. One of the examples that we're going to look at is the human blood. It has to be 7.4 all the time. Our blood really can't fluctuate a whole lot. If it falls by as much as 0.3 pH units, then death usually occurs. And 0.3 is not a lot. So it is in terms of pH. But it's not when we're talking about it, you know, if you guys lost 0.3, you know, of $1, you wouldn't be crying over that. But if you lose 0.3 pH units one way or the other, if it rises too much or it falls too much, so you're talking about 7.7 or 7.1, something around those are deadly numbers to us, which is pretty amazing that you can drink orange juice and milk and coffee and anything else you put in your body, and yet your body's going to just magically and amazingly fix its own pH. It will send out the right amount of the opposite. So if it becomes too acidic, it will send out a base. If it becomes too basic, it will send out an acid to balance those out. So the blood system in our body maintains a pretty constant pH of 7.4 because it contains buffers, which are the H2CO3 acid and the HCO3 conjugate base. If the blood becomes too acidic, which buffer do you think is going to be released? So if you're too acidic, are you going to release more acid or are you going to release a conjugate base? And the answer is it's going to release the conjugate base. And the cool thing is you don't actually have to think about it. You don't have to say, could you please do that? It just does it. Physical properties of acids, and y'all take a good look at that chart at the bottom. That's your pH scale. I think the only thing that seems to have confused students in the past is that they want to seem to think that that 0 means that it has no acidity, and that's not true at all. The closer you get to that 0 down there, the crazier strong acids you have. So acids, for example, you always think of that. Just remember when somebody says like a citric acid or citrus fruit, remember when you were little in elementary school and you guys built clocks by running them off of a grapefruit or a lemon or something like that? They have to have acid in order to do that. Okay, so acids, bases can also burn, but acids have a sour taste. They can burn your skin. They are soluble in water. That means they will dissolve in water. They are conductive, which is, think about how you guys made your little, working radio clocks or things like that by plugging them, so to speak, into a grapefruit. And they have a pH between 0 and 6.9. They have more hydrogen. So if you look at the left side of your chart, that's more hydrogen. The right side of your chart towards the 14 is more hydrogen. And keep in mind that that chart can go either way. They might put the 0 on the other side. If you go towards 0, you have more hydrogen. If you go towards 14, you have more hydroxide, OH. Physical properties of bases. They are bitter. They can burn your skin. They are soluble in water. They are conductive. They do dissolve fats and oils. They are slippery, and they have a pH between 7.1 and 14. And if you'll notice, the reason that there's a picture of a soap bar on the left-hand side, and also notice that it says that they dissolve fats and oils. Think carefully, what do you think that means the majority of the household cleaners that you have at your house would be? Think about all the things that you guys clean your house with. That means most of them are bases. The reason we use them for cleaning is because naturally, bases dissolve fats and dissolve oils. The chemical properties of acids, they react with other metals. They also react with bases. And they react with carbonates, which is how you get those really pretty things that you guys see when you go into, caves. Chemical properties of bases. And then we have indicator solutions. Indicators are dyes that change their color to show acidity or alkalinity. Remember, alkalinity is a base. It's how basic something is. And not basic by the new definition of she's so basic. I mean basic as in it has a pH between 7.1 and 14 and it dissolves fats and oils. Indicators are qualitative because they show acidity or alkalinity by changing color. That's the little strips that you guys dip into the liquid or whatever substance you're looking at. Generally, it's going to be aqueous if it's an acid or a base that you're testing. And they're just going to change colors. And so if you guys are doing that lab, you might be arguing and go, well, no, I think that's one color and so thinks it's another. And that's why we say it's qualitative. It means they're a little bit subjective because my idea of orange might be your idea of yellow. Litmus paper, blue litmus paper and red litmus paper. So acids always, if you have a red litmus paper, if you're starting with red, it keeps your red litmus paper red. In other words, it's not going to change. It's just going to look wet. Acids turn blue litmus paper red. Acids turn everything red. Bases turn red litmus paper blue, and they turn blue litmus paper blue. And I say they turn it blue because they don't change it to another color. So base is blue, okay? And if red litmus paper stays red and blue litmus paper stays blue, then it's just neutral. And then we have more specific ways. That'll just tell you if something, so I'm sorry, if you back up. If you're looking at red and blue litmus paper, that does not give you a reading of a number. It's qualitative, meaning that it just says it is an acid or it is a base. It's a qualitative thing. pH paper, on the other hand, can give you a more quantitative number, although it's not specific. You would need a probe for that. So it'll give you a ballpark range. Acids are going to turn pH paper from red to an orange color. And then if you look up at this in the top right-hand corner right here, look at that. If you look up right here and you see the papers where it says 4.5 to 7.5, you would have to take your paper and compare it to the colors that are on this or on the other side of this container here would have another side. It would have another chart on it. You compare it and you look and go, oh, well, it lines up with this color, so it's this number. So, for example, if it turned it from red to an orange color, you would look on here and go, oh, well, it must be maybe a 5.5. And that's how you would figure that out. Bases are going to turn your blue paper from a blue to a purple. So somewhere in that blue-purple range. And then neutrals, just keep it green. Phenolphthalein, you guys need to learn how to say it and learn how to spell it. It is an indicator solution. It's kind of my favorite. It just looks cool when it goes into an acid or a base. But bases are going to turn phenolphthalein pink. Acids really don't do anything to phenolphthalein. And here's some examples of vinegar, milk, soda, some examples of acids, sorry. Vinegar, milk, soda, aspirin, citrus fruits. One of the more popular cleaners that has kind of come onto the market lately at home is the use of vinegar combined with Dawn. Dawn is a regular soap. It is a base. Vinegar, unlike any other home cleaners that we usually use, most home cleaners are bases. Vinegar, on the other hand, is a pretty weak acid. So it's the combination of the weak acid, acetic acid in vinegar, and the base in soap that allows them to be good cleaners together, and it will eat up soap scum and stuff like that, especially off of like plastic shower doors and things like that. Bases, some good examples of those: ammonia, which is the active ingredient in Windex, if you guys use Windex as a window cleaner. Lye, antacids, which makes sense, right? Because an antacid is what you take when you have stomach acid that's bothering you. You have your stomach acid is rising up too far up your esophagus and it's giving you heartburn. So we say that it's burning you. So you take an antacid because it would neutralize your stomach acid. And then baking soda is another one. And then neutral substances have a pH of approximately 7. Pure water is usually around 7.4. They have the same amount of hydrogen ions as hydroxide ions. And we're going to stop for there. You guys can look through this for neutralizations.